The Hall effect is the subject today, and you might think the Hall effect is something to do with the echo in this hall. That's what, at first sight, it seems to be, but it's a thing named after Edwin Hall, who invented the idea in 1879 that you could actually get some funny effects from a magnetic field near a wire. So let me show you about that. Before I talk about the Hall effect, let me explain something else, which is called the Lorentz force. And in this apparatus, I have electric charges coming out of here, and they ionize the gas and make it glow green. So you've probably seen something like this before. Now, this is a magnet, a really strong magnet. So this is put in a little, I don't know, 36mm camera so that it doesn't clang against other things. And if I put that close to this, you can see that the beam of electrons coming out of there, giving that green glow, is deflected. It goes up if it's near this pole, and it goes down, if I turn it round, for the other pole. So the effect of a magnetic field, if the electrons are running this way, is to bend it upwards. Now, I could do the same experiment, this one, and now I put a sheet of metal, this is aluminium, and I'm going to put this sheet of metal in the way of the magnet. Now, have you got the beam still there, Brady? Because I'm going to put this close to the metal, and I'm not cheating you. Take the metal away, it's still there. Put the metal there, and it's still bending. The magnetic field goes through the metal. Any metal, when it's behaving normally, will allow magnetic fields to penetrate it. The question posed by Edwin Hall was, what happens if you have an electrical current down a wire, as in these wires, but I've blown it up so you can see it quite clearly, and I put a magnetic field near it. Now then, you've seen already that if there is an electric charge running along in this direction, a magnetic field will make it bend. So the charge is going along here, and it's going to go and bend, and suddenly it hits the wall. So if I now think about a wire such as this without a magnetic field, and let's pretend this is a charge carrier so you can really see what's going on. I mean, this is not really to scale. Here's a bit of the wire, and the charge goes through here, flowing down the wire, and the current is just the number of charges moving down the wire per unit time. So if I put a magnetic field down here, and the charges are coming along, as you've seen from this experiment, it's going to bend up and come to rest on the edge of the wire. And if I do this straight off, and then send another one down, it too will do this. Well, now I've got negative charges there, so I'll cancel them out with positive charges over here, and down will come another one, and it will suddenly say, oh, I want to go here, and there will be a positive charge induced on the other side. So now when another charge comes along, it wants to be attracted this way because it wants to go near the positive charge, but on the other hand there's a magnetic field which wants to sweep it that way, and the balance of these two means that it doesn't choose to go that way or that way, it just carries on down the middle, not being attracted to either side. And as a result, after these charges are built up on one side and the other, it gets to the steady state. So more and more charges can come through just as if this wasn't there. So there's no reason to expect that there's any effect at all. The current carries on flowing. It's just like water going down a tube. You don't know that there's anything happening on either side. The upshot of all this is the magnetic field does not affect the current going through the wire, but you now get, between the negative charge and a positive charge, a difference in electric potential, which you can measure using a suitable meter. So the idea is this: you send a certain current through here, and you measure this voltage from one side to the other. This is not the same as Ohm's law, where it's the voltage down the wire. It's the voltage across the wire that you're measuring. It's quite different. And this is the idea that Hall came up with. So you can measure this voltage divided by this current, which has a unit of resistance, because it's a voltage times a current. But it's nothing to do with Ohm's law. This is the Hall effect, a voltage this way with a current flowing that way. You probably want to know, Brady, what the use of this is. Well, I can get some very clever modern electronics, if I can turn this thing on, and you know how I am, Brady. I'm a theoretician. I touch pieces of apparatus and they break down, so this might take a little while to work out. Right at the end there's a tiny little square, about 1 millimetre square or a bit bigger, and wires go into and out of it, and that is the Hall probe. This small little square is the analog of this big one. And there are currents going into it, and there is a voltage across it. So if I put this in a magnetic field, and I put that in there, and you suddenly get, oh, it's gone off the screen. You can measure this in Tesla. That's 100 millitesla in there, and if you get in the middle, it goes off the scale. So you can actually wander around the room with this and measure the magnetic field in any particular direction. So if I have the square like that, it's a magnetic field coming in perpendicular that you're measuring. And if I twist it round, I'll get a different magnetic field. So you might want to invent things using this. And one of the things which is used using this effect is a burglar alarm. You put a tiny little magnet in your door, apparently, and a hole probe in the jamb, and set it all up with electronics, and as soon as the burglar comes in the door, this moves away from the magnet, and there's a huge change in the magnetic field, and you get a nice current. And nobody sees that you're doing it.
Cyclotron. One of the most interesting applications of motion of charged particles in electric and magnetic fields is the cyclotron. It is a machine used to accelerate charged particles. E. O. Lawrence and M. S. Livingston invented this machine in 1934. Let us first try to understand what a cyclotron is made up of on a fundamental level. Well, to start with, we have an electromagnet which continuously generates a magnetic field as shown here. Here, the magnetic field goes from the bottom to the top. Inside this magnetic field, we have two metallic plates, D1 and D2. They are also called Ds, as they are in the shape of the letter D. Both these magnetic fields are connected to an alternating electric source, which changes the polarity of the electric field periodically. Now imagine a charged particle P. A proton, for example, is at the center of this cyclotron. This proton will be attracted towards the negative plate, D2. As it enters the plate, it is acted upon by the magnetic field, and we know that a charge moving with a velocity v perpendicular to the magnetic field B will move in a circular fashion. As soon as this proton exits the plate and enters the gap, the polarity of the plates changes, and D1 becomes negatively charged. Hence, P will now get attracted towards D1 and will accelerate towards it. This increases the energy of the particle P. As it enters D1, due to the magnetic field, it will start moving along a circular path. But this time, as it got accelerated while entering, the radius of the circular path will be more. Again, as it exits D1, the polarity gets reversed, and now D2 gets negatively charged. Hence, P will now get attracted towards D2 and will accelerate towards it. This increases the energy of the particle P further. As it enters D2 due to the magnetic field, it will start moving along a circular path. But this time, as it got accelerated while entering, the radius of the circular path will be more. This cycle continues, and the particle P keeps on moving spirally. To maintain this spiral movement, the polarities of the Ds has to be reversed in a time interval t by 2. Where t is the period of revolution of the particle. T equals 1 by Vc, which equals 2 pi m divided by q times b, or Vc equals q times b divided by 2 pi m. This frequency Vc is also called cyclotron frequency. If we denote the applied voltage as Va, then the requirement is Va equals Vc. This condition is called the resonance condition. Once the particles are accelerated to the required speed, they are then deflected using a magnetic field. They then leave the system via an exit slit. This accelerated particle can then be used for bombarding other atoms, molecules or solids according to the requirement. We know that V equals Q into B into R by M. Here, R is the radius of trajectory of the particle at exit. This radius is equal to that of the D as well. The kinetic energy of the particle is half mv square, which equals q square into b square into r square, divided by twice the mass. The important fact here is that the time for one revolution of the charged particle is independent of its speed or its radius of orbit. This was a schematic of a cyclotron. In reality, it appears as shown.